times dx at x0 equals 3, and so on. But of course now you can kind of guess what this coefficient is. This coefficient is just 2x minus 3. So instead of writing an infinite list of answers for different values of x0, I just write the formula in one stroke. I just write one formula which is responsible for all of this. I just write df is equal to f prime of x dx. Yes? Yeah, well, it's like, when you're, certain things are allowed when you become adults, right? I mean, so that's sort of it's the same reason. It has to simplify things, but it leads to incredible confusion, in my opinion. So that's why I'm trying to unravel the precise definition and then explain how do we actually arrive at the formula which you see in the book. And I agree, in some sense, we should not be allowed. Or more precisely, we should be mindful of this. So whenever we see this formula, that's what we should see. We should see not a single formula, but a bunch of formulas which depend on x0, on choice of x0. That this one formula is not just one equation, but it's a collection of equations. For each value of x0, there's a formula which says that df relative to that x0 is f prime at that x0 times dx at that x0. And this formula is nothing but just saying z minus z0 equals f prime of x0 times x minus x0, which is the equation of the tangent line. But we write in one formula, we write down all equations for all tangent lines. That's what we do. You see? So that's the point I'm trying to convey here. Okay? And that's why I give examples. So maybe in this case, I would actually want to write more precisely. In this particular case, I will write f prime of x. I have found it, right? I have found that f prime of x is 2x minus 3. So in fact, I will write df is 2x minus 3 times ds. So more precisely, it is this formula which is responsible for all of this. Because if you have this formula, you will get this one. If you substitute instead of x, you substitute value 1. Right? If you substitute 1, you get minus, like I put. If at x equals 2, you will get 1. At x equals 3, you will get 3, and so on. Right? So this one formula will give you all of them. In other words, I give you this formula, you should be able to substitute any value x0, and you will get the equation of the tangent line at that x0. Does it make sense? Any other questions? Okay. So there's nothing mysterious about the differential. The only mysterious thing is that it should actually be defined relative to a particular point x0. And what we have done, or people before us have done, is that at some point they decide to drop this from the notation. So the formula starts looking like this and starts looking very confusing because what does it mean? What is df? What is dx? It becomes very, very confusing. But if you remember that it actually refers to a particular value x0, and once you remember that, you know that dx corresponds to x minus x0 and df corresponds to z minus z0, then the mystery disappears. There's no mystery. It becomes an extremely simple and mundane formula, just a formula for the tangent line, the equation for the tangent line. That's what it is. Okay. So one more piece of notation to sort of finish with this. We can also write delta f. So that's sort of to make things even more confusing. There is also notation delta f. Okay. And delta f, and again to be precise, we also have to say that it's relative to some x0. This, by definition, is f of x plus x0 minus f of x. So it is the increment of the actual function. It is the increment of the actual function, whereas df is the increment of the tangent line, of the linear function which approximates our function, you see. So that's the difference between the big delta and small d. So this should not be confused. With df relative to the point x0, which is f prime of x0 times x minus x. Let me draw again the picture. Let me magnify. Actually, let me not draw the coordinate system, but let me magnify, blow up the small neighborhood of this point. So here's my graph, and here's my tangent line. So here is x0 somewhere, and here will be x. Here will be I'm sorry, I wrote something correctly. X minus x0. Sorry. F of x minus x. So there is x0 and there is x. Oh. So now I'm trying to confuse you. I'm sorry. Yeah. I was going to draw it on the picture anyway. So look. This is delta f. You see what I mean? This is x0 and this is x. And x is very close to x0. Okay. I can measure the value of the function itself, which is the yellow curve. I can measure the difference between the values of the function. That's this, right? Or I can measure the difference between the values of the linear approximation, the linear function, which corresponds to the tangent line. That's df. Okay? You see what I mean? These are different because it doesn't quite go up to here. They start diverging. They start deviating from each other. But the punchline is that they are almost equal. The difference is negligible. The closer you get to this point, the closer x and x0 are, the smaller the difference is going to become. Right? That's the punchline, which expresses the fact that linear approximation is useful in the following sense that when you're very close to the point, your linear function, whose graph is the tangent line, is almost as good as the original function. In case, of course, your function is a nice one like this, so it's kind of a smooth function. And such functions for which this linear approximation works are called differentiable functions. And so the punchline of all of this discussion is the following, that there's a large class of functions, f, for which the difference between delta f and df is negligible. It's very small. Relative to, it's much smaller than the difference between x and x0. So we can actually ignore it when x is very close to x0. So the notation is different, but the point is that the two quantities for differentiable functions are very close, which is to say that a linear function, the function which gives you the tangent line, is a good approximation to the original function. Let me write this down. So function f of x is called differentiable at x equals x0 if delta f at x0 equal to df relative to x0 plus, I promise you not to use epsilon, but let me use it anyway. So to indicate that it's something very small. But I will not use delta. So where epsilon of x goes to 0 as x goes to 0. So in other words, this piece is negligibly small. You see, because this already goes to 0, and this certainly goes to 0 when x goes to x0. So this goes faster than x minus x0. It goes to 0 faster than x minus x0. So this is precisely what I indicated by that little difference. Maybe let me point out this. This little piece, this is what is epsilon of x times x minus x. It's a very little one. This tiny little piece is something that goes to 0 faster than x minus x0. This already goes to 0, and this goes to 0. So it goes as a square. It roughly goes as a square of x minus x0. So let me unravel this for you. In other words, what we're saying, the function is differentiable. That's the expression. If delta f is df plus this, so what is delta f? I explained that delta f is just f of x minus f of x0. So let me just spell out what that formula means. Let me call it star. Okay? So formula star is just saying the following. This, and now I want to spell out what df at x0 is. And df at x0 is this, right? So it's f prime x0 times x minus x0 plus epsilon of x. Now, if you remember Taylor series, this gives you a good perspective on this formula. Do you remember Taylor series? Okay. What? You don't want Taylor series? How about just the first two terms in Taylor series? Okay. I'm not asking for more than that. In Taylor series, the idea was that the difference, that f of x, the idea was that f of x is equal to f of x0 plus f prime of x0 times x minus x0 plus 1/2 f double prime x0 times x minus x0 squared plus and so on. Okay. So I just want to explain to you what we are doing now. We are just looking at the first two terms of the Taylor series. We are just focusing on the first two terms of the Taylor series because this one term is this. Okay, now it's on the left-hand side, but big deal. We can just rewrite it like this. Let's take it to the other side. So you see, this matches this term matches this. In the Taylor series, we then have all the higher derivatives and higher powers of x minus x0, square, second, third, and so on. And now I have taken all of this stuff and just denoted it by this one expression. Because see, the main point is that the powers of x minus x0, which show up in this term, the next term, are 2, 3, 4, and so on. They are higher than 1. So I can sort of chip off the first power, x minus x0, and what will remain, for example, here, it's like second power. So this will have, I just split x minus x0 squared into this, and one more x minus x0. So in other words, this thing also goes to 0 by itself. You see what I mean? What I'm doing roughly is, let's take this term, 1/2 f double prime of x0 times x minus x0 squared. What I'm doing is just I'm writing it like this. I mean, I've done nothing. I just wrote the square as a product. And after this, I take this piece and call it epsilon. So then what I get is epsilon times x minus x0. The point is that this guy by itself goes to 0, right? It goes by itself to 0 because this is finite. This is just some expression, for example, for the function which I had, which was the first derivative was 2x minus 3, so second derivative would be 2. So this is just some number which is 2. And it's 1/2 of 2, so it's just 1. But then there is x minus x0. X minus x0 is something that goes to 0 as x approaches x0. But in addition, I have one more power, x minus x0, because I started out with the second power. The only term for which this will not be the case is the first term. In the Taylor series, the first term will have x minus x0 to the power 1. And that's the one which I retain. And then everything else, I say everything else is really negligibly small compared to this term. So that's the idea. That's the main point of our calculation now. Before, we try to write it as an infinite series, which involves all powers. Sorry, all derivatives of the function. It involves no derivative at all, the first derivative, the second derivative, and so on. What we are saying now is that how about let's just keep the constant term, which is f of x0, and let's keep the first derivative term, right, which gives rise to the linear term in x. Let's just keep this, and everything else we'll just put in the back and call it epsilon of x times x minus x0. It's something very small times x minus x0. So it's negligibly small compared to the first two terms. The special thing about the first two terms is that they give you a linear function, which is a function whose graph is a tangent line. Right? So writing down this formula means that you approximate your original function f of x by a linear function. By a linear function. This one, plus some really, really small, negligibly small error term. That's what we've done. Okay? Questions? Yes? That's right. So I'm talking about functions in one variable, right? Because I'm of the opinion that before you do complicated things, you should start first with a simple thing. And this is a case of one variable. So I want to explain everything in excruciating detail for functions in one variable. So now we'll have to talk about functions in two variables, right? But the point is that everything is going to work in exactly the same way. And I believe that you first have to understand what happens for one variable. And only then you'll be able to fully understand what happens for functions in two variables. So let me explain now functions in two variables. What happens for functions in two variables? So, what can I erase? I want to keep this, and I kind of want to keep everything, but all right. Let me erase this. So now we have a function in two variables, x and y. So we have f of x, y. So see, aren't you glad I haven't used y in the previous, calculations? We had x and z. Now we have x, y, and z, right? So now we're going to have a graph of this function, but in space, and that's going to be a surface. So let me try to draw this. I will draw it in a slightly different way than last time because I think it will be a little bit more clear. But you tell me, like this. I want to draw it like this. No. Okay, like this. And now we have a point. And now I want to say that there are two curves here, which actually last time I drew them with red and blue, but okay, let's not worry about this. So this is one curve. And that's another curve. Maybe I can do it like this. It's better like this. You see, Picasso is never satisfied, you know, his drawings. Okay, something like this. I think it's better. You see what I mean? It's kind of it's a surface like this, but it's concave. Last time I drew it convex like this, and now it's concave. I think it's a little bit easier on the eyes, so to speak. So this, of course, all lives in three-dimensional space. So there is a three-dimensional coordinate system, as usual, x, y, z. And this corresponds to a particular point with coordinates x0 and y0. You see? And now I want to draw the analog of the tangent line. So this yellow thing is the analog of this of the curve, of the graph of the function. When I say yellow thing, I mean, of course, the whole thing. The surface, right? You see what I mean? Okay? So now, before I had a tangent line because it was a curve. So for a curve, it makes sense to talk about a tangent line. But for a surface like this, it makes more sense to talk about the tangent plane. It is two-dimensional, so in your linear approximation, you should use a linear surface, but not a curve, a linear surface, which is what we call a plane. So, in fact, I brought something to illustrate it even more. So, this should play the role. I tried to find a basketball in the math department, but finding a basketball in the math department is like, well, you complete the sentence. It was difficult. So this is what I found. So this is a surface, and I just want to explain what the tangent plane is. The tangent plane is what? Is a plane, let's say if I pick a point. The tangent plane is a plane which is the closest plane to this surface, right? So that's the first point I want to make. And the second point I want to make is that tangent plane is going to change when you change the point of contact. If you're interested in the tangent plane at this particular point, that's the plane you have. But if you want at this one, that's going to be this one, right? So it's exactly the same thing as we have for curves, for tangent lines. Tangent line depends on the choice of the point. Okay? Now, let me draw this tangent line for you. So you see, to indicate to give sort of more shape and volume, well, not volume, but really the two-dimensional aspect to this, perspective to this, I drew these two curves. What are these curves? These are the curves, exactly the same curves that I drew last time. This is a curve of intersection. This is intersection with a plane which goes like this, which is parallel to the YZ plane. So it's really the plane where we fix the x coordinate, x equal x0. You will see that what I'm doing now is very similar to what I did last time, but there are small differences. For example, the graph I was using was convex in a different way. Also, instead of x0, y0, I used notation AB and so on. But otherwise, it's very similar to what I did on Tuesday, right? And so what I do is I can cut by a plane, a vertical plane like this. I can cut the graph by this vertical plane which is parallel to YZ, and that's the curve I get. This is a curve which lives on the graph, on the surface, on the vase, if you want. So this is like part of the vase, and this lives on the vase. And then there is a perpendicular one which I get by cutting it by a plane which is parallel to the XZ plane. That's this one. The only thing is I confused them, right? I think it's it. What I was trying to say is that this is the curve you get by cutting with the vertical one parallel to ZY. And now this one is what I get by cutting with the plane parallel to XZ. So this curve is intersection with the plane y equals y0. So the graph is complicated. The graph is a surface, but on this graph, for my point x0, y0, I have drawn two curves which in some sense are perpendicular to each other. These are the curves of intersection of the graph with two natural planes, two vertical planes. One plane is parallel to the blackboard, that's this one, and the other one is parallel to this one, which kind of has an angle too, which really, since I'm just giving it a three-dimensional perspective, but I'm drawing it like this. But in fact, you should realize that it's a plane which should be perpendicular to the blackboard, this xz plane. Okay, so I get two curves. Now, curves is something I can handle because we now know everything about curves. We know everything about tangent lines to curves. So these two curves have tangent lines for sure, just like this curve has tangent line at our point, right? So let me draw two tangent lines. One will be the tangent line to this curve of intersection, and the other one will be the tangent line to this curve of intersection. I'm kind of trying to separate them a little bit, so that's why you see as though there's some distance between them, but there should be. Just make it more visible. Okay? And now these two planes, these two lines, in fact, they span a plane, which looks like this. Right? See, that's the plane which is kind of slightly underneath the graph. That's what I was illustrating when I put a vase here, right? And that would be the tangent plane. So on this tangent plane, I would have two lines. These two lines, which are tangent to the intersection, to the curves on the graph, which you get by intersecting the vertical planes. You see what I mean? Is this clear? That's right. It's a tangent to that particular point. Exactly. If I take